Hello, welcome to another module in this massive open online course. In this module, we will start looking at a different concept, that is group and phase delays of an LTI system. Okay, so we want to look at another important topic, a small topic, which is known as how to characterize the group delay as well as the phase delays, the group and phase delays. And so to do this, consider an LTI system. Okay. Consider an LTI system with impulse response Ht. Okay. And therefore, what we have is we have the LTI system with input x of t, output y of t. The impulse response of the LTI system is h of t. So, this is your input, this is your output. Okay. And let us say this transfer function of h of t as the transfer function as the Fourier transform h of omega. We know this is also known as the transfer function, correct, of the LTI system. Now, what happens in this is that we have, I can write y of omega, the frequency response of the output is basically x of omega times h of omega, alright. The output is basically a convolution of the input signal with the impulse response, which means in the Fourier domain it is a multiplication of the input Fourier transform x omega with the transfer function h of omega. Okay. Now, let h of omega equals the magnitude of h of omega times phi of omega, where phi of omega is the phase response. This is the angle of h of omega. Now, what we do is consider a sinusoidal carrier x of t equals a cosine omega naught t. So, this is basically your pure sinusoid. Okay. So, just for the purpose of illustration, you consider a pure sinusoid a cosine omega naught t. Now, this is given as input to the LTI system. Okay. It's given as input to the LTI system. Now, we have already seen y of omega equals h of omega into x of omega. Now, what is x of omega? X of t is a cosine omega naught t, which means x of omega we know from the Fourier transform, that is a times the Fourier transform of cosine omega naught t. So, this will be pi a delta omega minus omega naught plus pi a delta omega minus omega naught. Okay. That is the response, or that is the spectrum of a cosine omega naught t, two impulses at omega and minus omega naught, alright, omega naught and minus omega naught scaled suitably. Okay. Now, y of omega equals h of omega into x of omega which is equal to, well, h of omega into pi a delta omega minus omega naught plus h of omega pi a into delta omega plus omega naught, which is equal to, well, when h of omega into delta omega minus omega naught, that is simply h of omega naught, you can say pi a h of omega naught delta omega minus omega naught plus pi a h of omega naught into delta omega plus omega naught. Now, let us consider a real filter, alright, filter with real impulse response h of t, which implies h of omega naught is h conjugate of minus omega naught. Oh, I am sorry, this has to be h of minus omega naught. Okay. So, considering a real impulse response h t, we have h of omega naught is h conjugate of minus omega naught. Okay. So, we have for real h t, when h t equals real, this implies h of omega naught is h conjugate of minus omega naught, which implies if, since h of omega naught is magnitude h of omega naught e raised to j phi omega naught, h conjugate or h of minus omega naught is h conjugate of omega naught, which means it has the same magnitude and negative phase e raised to minus j phi omega naught. So, now substituting this above, this implies your y of omega equals pi a magnitude h of omega naught e raised to j phi of omega naught, that is h of omega naught, into delta omega minus omega naught plus pi a into magnitude h of omega naught times e raised to minus j phi omega naught into delta omega plus omega naught. And now, if you look at this response, this is interesting, it can be simplified as follows. This will be pi a, take the magnitude of h of omega naught common. If you take the inverse, take the inverse Fourier transform, and you will observe something interesting. This pi a magnitude h of omega naught times e raised to j. Now, look at this, this is delta omega times delta omega minus omega naught. So, pi delta omega minus omega naught, that will have the inverse Fourier transform half e raised to j omega naught t times e raised to j phi omega naught plus a times magnitude h of omega naught e raised to minus j phi omega naught times pi delta omega plus omega naught, that has the inverse Fourier transform half e raised to j or minus j omega naught t. So, as a result, this will simply be your a times magnitude h of omega naught times e raised to j half e raised to j omega naught t plus pi omega naught plus half e raised to minus j omega naught t plus phi omega naught. Okay, and therefore this will be equal to a magnitude h of omega naught times, now half e raised to j omega naught t plus phi omega naught plus half e raised to minus j omega naught t plus phi omega naught is simply cosine omega naught t plus phi omega naught. So, that I am going to write over here. So, that is cosine omega naught t plus phi omega naught. And now therefore, you can see this is simply has a phase difference. So, original carrier is, so this is your scaling, okay, this is your gain, you can say this is the gain due to the LTI system, and this is the phase offset. So, when you input a pure sinusoid, as you know, to an LTI system, you get the output is also pure sinusoid. This is the gain magnitude h of omega naught, and this is the phase offset phi omega naught. And this I can write as a times magnitude h of omega naught times cosine omega naught t minus or t plus phi of omega naught divided by omega naught, which is equal to a magnitude h of omega naught cosine omega naught t minus phi of omega naught divided by omega naught, and close the brackets. And therefore, now if you denote this quantity by tau p, by the delay tau p, this will be a times magnitude h of omega naught cosine omega naught into t minus omega naught into t minus tau p. Okay. And this tau p is therefore a delay. So, what you are observing is you input a pure sinusoid, what you get at the output is another pure sinusoid with a suitable gain, that is magnitude h of omega naught, and a delay tau p. This tau p is known as the phase delay of the system. So, if you input a pure carrier, the delay in the resulting carrier is known as tau p, that is the phase delay of the system. So, this is basically your and the phase delay tau p equals minus phi of, and in fact this phase delay you can see is a function of omega naught, it is function of the frequency. So, this is minus phi of omega naught divided by omega naught. Okay. So, this is basically the delay of a carrier this is delay of the carrier input to LTI system, and this is termed as your phase delay. Okay. This is termed as the phase delay of the system. Okay. Okay. So, the phase delay of the system of an LTI system is basically minus phi omega naught divided, the phase delay at carrier frequency omega naught is minus phi omega naught divided by omega naught, where phi omega naught, remember this is the frequency, this is the phase response of the LTI system. Okay. So, phi omega naught, the other thing to remember is this is the phase response of the LTI system. And group delay, now let us now consider the other aspect, that is the group delay. Now, the group delay, to illustrate the group delay, we consider a modulated signal, that is a pure carrier modulated by a message signal. So, consider a modulated signal. So, to illustrate the group delay, basically consider a modulated signal. Consider a modulated signal, we have x of t, we have x of t equals a cosine omega mt times cosine. So, previously we simply had a pure sinusoid, that is a times cosine omega naught t. Now, we are also considering a message signal, correct. So, this is your message signal, and this is in fact very similar to a communication system in which you modulate a message signal with a carrier frequency. So, you have a cosine omega mt, that is a message signal, and cosine omega naught t, you can think of it as the carrier. Okay. So, this is basically your carrier. Carrier signal or simply the carrier at a very high frequency compared to the. Now, the thing about a communication signal when a modulation is that omega naught is typically much larger than the message frequency. The carrier has a carrier is much higher than the bandwidth of the message signal. Okay. So, carrier frequency is significantly larger than the message bandwidth. For instance, you can look at a typical AM signal, which is carrier frequencies of thousands of kilohertz. The message bandwidth is typically only of 10 kilohertz or multiples of 10 kilohertz, right, tens of kilohertz. Okay. So, the carrier frequency is typically hundreds of times larger than the the bandwidth of the message signal. Okay. All right. And therefore, now I can write this signal xt using the properties of trigonometric functions. I can write this xt as a by 2 cosine, well, this will be omega m minus omega naught t plus cosine omega m plus omega naught omega m plus omega naught times t. Okay. And this you can think of this as this omega m minus omega naught, you can think of this as basically the low frequency, right. So, you have two frequency components, omega m minus, or in fact you can write this as omega naught minus omega m, does not make a difference because cosine of minus x is cosine of x. So, omega naught minus omega m equals the low frequency omega L, omega naught plus omega m is the higher frequency component equals omega h. So, this is basically your a by 2. So, what we have over here is a by 2 cosine omega L t plus cosine omega h t. Okay. So, basically now what you have, because you are modulating a sinusoid omega mt with much smaller bandwidth with a carrier that has a much higher bandwidth, that gives you two resultant sinusoids. One is at the lower frequency omega L, which is omega naught minus omega m, and the other which is at a higher frequency omega naught plus omega m. Okay. And now we pass this through the LTI system, Now, you pass this through the LTI system. Now, the output corresponding to A, remember we have already seen this all we have here is previously we have omega naught, previously we had a cosine omega naught t and we are passing it to the LTI system. Now, we simply have a by 2 cosine omega L t, alright, a pure sinusoid at a different frequency omega L, and therefore, the output corresponding to this pure sinusoid of the LTI system can be easily written as, the output will be a by 2, as we have seen before, magnitude h of omega L times cosine into cosine of omega L t plus phi of omega L, where phi omega L, as you know, is the phase response of the phi of omega is the phase response of the LTI system. Alright, this we have, this follows from what we have already seen before. Okay. Now, similarly, the output corresponding to, well, the output corresponding to the higher frequency component, similarly, if you look at a by 2 cosine omega h t, so the LTI output, and the LTI output corresponding to a by 2 cosine omega h t is magnitude h of omega h into a by 2 times cosine omega h t plus phi of omega h. Now, the net output of the LTI system will be the sum of these two outputs, implies net output equals a by 2, well, that will be magnitude of h omega L cosine, well, omega L t plus phi omega L plus magnitude a by 2 cosine omega h t plus phi omega h. Okay, so, this is what we obtain. Now, notice that omega L equals omega naught minus omega m and omega h equals omega naught plus omega m. And further, what we have is omega m is much smaller than omega naught. So, the difference between omega L and omega h, you can see, is 2 omega naught. So, omega L and omega h are separated by 2 omega naught. Omega L and omega h are separated by 2 omega m, but omega m is a very small quantity compared to the frequency. Therefore, the frequency response, the amplitude, the magnitude response of the LTI system, magnitude h of omega, can be assumed to be constant over this interval, that is omega L to omega h, meaning to say, that is, you have omega L minus omega h minus omega L is 2 omega m, which is much smaller than omega naught, which implies that you can assume that magnitude h of omega L is approximately equal to magnitude h of omega h approximately equal to magnitude h of omega naught. So, one can assume that the magnitude response, correct. So, one can assume that the magnitude response is the variation of the magnitude response of the LTI system is basically negligible over this small frequency interval, that is from omega L to omega h. Okay. Alright. So, this is that is basically variation. What we are assuming is the variation of the magnitude response is negligible over minus is negligible over the interval omega L to omega h. Okay, so this is negligible over the interval omega L to omega h. Alright. So, basically what we have seen in this module is we have looked at the phase delay and also started our discussion on the group delay. We will complete this derivation, alright, the developing this framework in the subsequent module. Thank you very much.